Rowden, and this is our project for dynamics. So we wanted to go ahead and figure out how much time was necessary to accelerate my mass with the skateboard's mass a certain distance. So we went ahead and figured that out by first taking down all our givens. So the first given is the mass. I weighed myself, and the board has a known weight, so we put it all together and converted it into kilograms to make everything easier in units. So I have a mass of 93.44 kilograms. We have a distance traveled of 16 meters. The power output of the board itself, the thing that will be creating the force pushing me, is going to be 500 watts. We're starting from rest, and at the end of the run, we achieved a final velocity of 4.58 meters per second. We attained that velocity by using a speedometer app on our phone.
Hi, I'm Matthew, and I'll be taking you through these lovely equations we have here today. Alright, so basically, we already know the power of the board, and we also know our final velocity. So we can use this handy-dandy equation, basically P equals FV. That's a short form. The actual calculus form is P is the integral of f dv, obtained by simply taking the derivative of our standard work interval. Doing this, we can also presume that our force is constant, and it probably is because we only went for a short distance, so we didn't put the motor through its higher end stages. Because of this, because the force is constant, we can take it out of the integral, and now we're just left with the integral of dv from 0 to our final velocity. So when we evaluate that, our initial velocity, as Mark introduced, was v0 is 0. Also, our final velocity was recorded as 4.58. And so we end up with P equals the force times our final velocity. From this, we know the power and we know the velocity, so we can find the force. Once we find the force, it's very easy to find the acceleration. Just use F equals ma. And then once we have our acceleration, we can easily find our time by using the kinematic equation x equals v naught times t plus 1/2 at squared. Because we started from rest, our initial velocity is 0, so we can easily find at by simply moving a and 1/2 to the other side and then taking the square root, leaving us with t equals the square root of 2a plus x.
So now that we went ahead and explained the equations, we can go ahead and see that once again, starting from the beginning, we have a need for a force and we have a need for acceleration. Ultimately, to figure out how long we took to get somewhere, we need to figure out the acceleration. So setting things to F equal to ma, having a known mass, and having known that we actually already have a power and a final velocity, we can actually solve for the force outside of this equation. So now that we have force known and we have calculated it to be 109 newtons, we can go ahead and plug that force back into this equation. So this is the same equation that was here. All we did was set A by itself and went ahead and divided 109 newtons by 93.44 kilograms, and ultimately that gave us 1.167 meters per second squared. So now back to the kinematic aspect. Now that we're down here, we have an acceleration. We have an acceleration and we have a distance. That is all that's necessary to solve for time in this case, because of the kinematic equation we chose. So you set t equal to the square root of 2a over x. So since we know acceleration and we know the distance, that gives us 5.24 seconds. As you can see right here from our collected results, this is actually what we went ahead and found while doing the experiment itself. So we found through an average of, taking the average of 7 runs, that our time to travel that distance of 16 meters was actually 5.25 seconds. So previously we were able to calculate and predict that the time was going to be 5.24 seconds. So as you can see, we actually had a very successful run, and we were able to accurately predict the amount of time it would take to carry a mass a certain amount of distance using just the power the acceleration, calculation, and kinematics.
Now, we did get a 0.3% error, and while this is very small, it's always wise to account for your percent error and where it could have come from. As such,
2, 1.
okay, so our percent error was 0.3%, and while this is a very almost insignificant amount that could also be attributed all the way to human error, it is always wise to account for other possible errors that could have occurred during the experiment. So other possible errors that we didn't account for would have been the energy absorbed by the rotation of the wheels. And so we didn't account for that because it was so negligible. The wheels are really small, and we don't know their radius of gyration, nor do we know their mass. Also, other potentials of error is that the ground that the experiment was conducted on, outside in the parking lot, the asphalt, is not perfectly smooth. Therefore, you get some normal forces on the wheels, and those normal forces also cause additional loss of energy.
There's also a slope potential. The area we're working on top of not being perfectly smooth is actually not perfectly flat. Although it is relatively flat, any amount of incline or decline is going to have an effect on the results.
And finally, one additional possibility of error is our deflection when we were conducting our experiment. We measured parking spaces and used those to consistently tell us how far we were going. However, those parking spaces may not have been arranged perpendicularly to our direction of travel.
So that is our project. Thank you very much, Dr. Gordon.